Hi, my name is Josephine Nwama, and this is Lab 1 of Physics 1 about constant velocity. The purpose of this lab is to observe an object's position at constant velocity, which means constant speed and no change in direction, through an experimental model using the Tracker software, and compare it to a predicted computational model of the object's position using GlowScript. So some of the general description is that our system will be a marker, our surroundings are the cement floor, gravitational force of the Earth, and then we will use Tracker and GlowScript to model. So before we get into it, we have to first understand some fundamental principles of what makes constant velocity, and we can do that by understanding Newton's first law and second law. Newton's first law says that an object at rest remains at rest and an object in motion remains in motion at a constant speed in a straight line unless acted on by an unbalanced force. We can see this in the diagram to the right, where the normal force and the gravitational force cancel each other out, leading to constant velocity based on Newton's first law. This can then be applied with Newton's second law. The net force applied onto a system equals the change in momentum over the change in time. So here we have a general formula of Newton's second law. We can rearrange it, and then we get a velocity update formula, which says that the final velocity equals initial velocity plus the net force times change in time over mass. So when the net force is equal to 0, we get constant velocity, as the final velocity is now equal to the initial velocity. The procedure involves recording a video of a marker rolling at constant velocity, recording its position over time on Tracker, finding its initial position, its initial velocity, and editing the GlowScript code and inputting those initial conditions of the marker, and then that way we can graph the observed and predicted positions of the marker and compare the data. Some assumptions we're making is that the net force is 0, and we're not considering air resistance and friction forces. The marker is also considered to be rolled on a flat surface, which means the position changes in the x direction, and the position and displacement in the y and z directions are constant. These are the main results, but let's go through how we got this. Here's a video of the Tracker software tracking the marker as it rolls. As you can see, the little diamonds are tracking it, and then you're getting the data on the side. So here's the analysis of the Tracker data. As we said, the y should be constant, so we're not looking at that column. The total time is 0.7 seconds, which is the amount of time after the marker left my hand and rolled to the end of the video. The initial position can be seen in the first row, where we have the x component at t equals 0, and our initial velocity can be found by change in displacement over change in time. We can use this equation because the time step is relatively small, between 0 to 0.033, and that can give us a good estimate of what the initial velocity would have been. So now that we have our initial conditions, we can change the code. Mass does not affect the velocity update formula because Fnet equals 0, so it just cancels it all out, so any number can be added there. However, the mass of my marker was 0.0105 kgs. Then we inputted our initial position and initial velocity, and have our Fnet equal to 0 because we know that's a defining factor of constant velocity. We have our time, and then our change in time is 1 over 30 seconds because that was the frame per second in which Tracker used to film the video. Now on this side we will be applying the momentum principle, so we have the velocity update formula, and then down here we have the position update formula, which can be seen above, and that is what GlowScript uses to then give us a predicted graph. So here we have our two models, the observed position done experimentally and the predicted position done computationally. Obviously the predicted position will be at constant velocity because it's done in the ideal scenario. However, initially the observed position is equal to the predicted position, but it slowly slows down as time proceeds, which means that the velocity is slowing down. This is likely because of other forces present, frictional, air resistance, and gravitational forces, that are leading to having an unbalanced force, which according to Newton's first law means that there would be a change in velocity. So the predicted position is overestimating the position of the marker because it doesn't consider any of the other forces that are applied in the observed position. Some possible sources of error would be not being consistent in our tracking points using Tracker, that other forces are present, including friction, air resistance, calculation errors, rounding, coding, human errors, and that the velocity was simply not constant when I threw it from my hand. And you can kind of see it here from the Tracker data that the velocity simply wasn't constant in the experimental model. So just to answer some discussion questions, what if the axes were switched? Velocity would still be constant, but the slope of the position versus time would be negative. The same conclusions, however, would still be reached, that the computational model would overestimate the position versus time. Secondly, is it possible for you to say how many pushes and pulls are added together to give zero net force? And it is impossible to determine because we don't know the magnitude of the forces on the object, such as gravity, friction, and air resistance interfering. and therefore, experimentally, the net force was not equal to 0, and thus had an unbalanced force, which according to Newton's first law, will lead to a difference in velocity. To improve this experiment, we can use an object that is more consistent in shape and a flatter surface to roll the object on to limit friction forces. Thanks!